All right, today we're doing 3-3, like part 2 here. I think it's 3. Yes, similar figures and scale. All right, so today we're going to start talking about more of the scale stuff. But before we get there, we're going to talk about the area of our similar figures and the volume of our similar figures. Okay, so the area of similar figures. The ratio of the areas of similar figures is equal to the ratio of the corresponding sides. Okay, so it's equal to the ratio of the corresponding sides squared. So let's look at that. That's what this is saying here. Our corresponding sides ratio is side A to side B. And that's how we set up our stuff, like just in the questions that we had. If we, oh, these are reversed. I'm sorry. This one should be up here with area. So my apologies when I set those up. So the area one is down here, right? Do you see area here? It's the same premise though. So the corresponding area ratio is just our ratio of the side lengths squared. So if the ratio of our sides was 1 to 2, our volume, our area here is going to be 1 over 2 squared, which is equal to 1/2 times 1/2. What is that?
1.
Well, 1 times 1 is 1. 2 times 2 would be 1/4. Okay.
How do you go from 2 halves to less?
Well, 1/2 times 1/2 is 1/4 because they're already smaller. So you're taking a half and you're cutting it, like you're taking a half of a half. No, multiplication doesn't. It doesn't. It doesn't get bigger, but you're taking, so you have something that's cut in half, and you're taking the half, right? And you're cutting the half in half. Well, I was trying to change color here. You're cutting the half in half. So now the piece that you have is actually 1/4, right? It would take 4 of those. Yeah, so it's actually smaller. So no, multiplication of fractions or numbers that are less than 1 or less than 1 but greater than 0 actually give you a smaller number even. Okay. All right. Then for the volume of our similar figures. So if we think about the volume aspect here, okay, the volume of similar figures is the ratio of the volumes of similar figures is equal to the ratio of the corresponding sides again, but this time it's cubed. Remember, that's the power of 3. So up here, if we do that same thing, okay, we have our corresponding sides ratio is A over B. So our volume is going to be A over B cubed. So again, if our ratio is 1/2, then for our volume, it's going to be 1/2 cubed, which means it's 1/2 times 1/2 times 1/2. 1 times 1 times 1 is 1. 2 times 2 is 4 times 2 is 8. So the volume is 1 over 8. So this means, what this means though, okay, is that we're comparing the area of two, like here we compared the sides of 2 different polygons or 2 different triangles. In this case, we're comparing their areas. So the area of this one to the area of this one, their side length would be double. Their area is 4 times bigger. The volume between these two, if it was a 3-dimensional shape, okay, the volume would be 8 times bigger. So if this one was, you know, the volume was 1 cubic unit, the volume of this one would be 8 cubic units. Okay. All right, I think we're shaking our heads, but I don't know that we understand. So we're going to look at those. So let's look at example 4. We have 2 similar rectangular prisms. Have corresponding edges. Let me change up here. Corresponding edges in the ratio 2 to 3. Okay. The area of the base of the smaller prism, so we're calling this area sub S, area of the smaller prism. Okay. But this is area, is 36 units squared. The volume of the larger prism, so we're calling it V sub L, volume of the larger prism, 1,215 units cubed. Whew. So A, I should have spread these out so we could do each of them as separate. Find the ratio of their areas and use a proportion to find the area of the larger prism's base, A sub L. Let's just start there and do A. We'll get to B in a minute. Okay. So it says find the ratio of their areas and use a proportion to find the area of the larger prism's base. So first part, find the ratio of their areas. Okay, we're going to take this ratio up here. We're going to put it into a fraction form. 2/3 or 2/3. Okay, and we want to find the ratio of their areas. So we're going to come back up here to where it talks about their area ratios. Because what do? If we have the sides ratio, what do we do with that to get the area ratio? We don't multiply by 2. We square it. That's it. They gave us the area, or they gave us the ratio of the edges or the sides. So all we have to do is to take that same ratio and square it, and we'll have the ratio of the areas. So 2/3 squared is going to be 2/3 times 2/3, which is going to equal 4/9. Okay, right there is the ratio of their areas. You just found it. Well, we're not there yet. Okay, we found the ratio of their areas. Okay, so now, so get that copied down. Because then we're going to use a proportion to find the area of the larger prism's base. Now we have to make 2 fractions. Yes, because that's a 2 fractions is a proportion. I'm with you now. Okay, we're going to use 4/9 because that's the ratio of our areas. Good. So we're going to take that 4/9. That's going to be one of them. It's going to equal 36 because we're taking the area of the smaller one. So we're going to use this 36 now. Good. All right, so here's the question. Does the 36 go with the 4 or the 9? Why the 4? How do you know it's in the same prism? Because of their reading. I don't know what that means, because of their reading. Give me more. Or do you guys agree with him? Does the 36 go with the 4? Okay. Okay. That's a good question, though. Why are we using the 36 units? We can go back to that. Okay. So let's see. All right, so we found the ratio of the areas. Now we want to use a proportion, okay, to find the area of the larger prism's base, which is A sub L. Well, they gave us some information about the area of the small base of the smaller prism earlier, or A sub S, is 36. So since we're talking about area, They gave us the smaller prism's area. We have to solve for the larger prism's area. Okay, but that's a V. The volume of the larger prism is V. So they gave us multiple pieces of information. Okay, so that's a good call. So they gave us the smaller prism's area. We have to find the larger prism's area. So in this case, I'm going to go back to this question. Does 36 go with the 4? Do you think the 4 is the larger prism or the smaller prism? The smaller. It's a smaller number, so it should be the smaller prism. So the 36 would go here, and our A sub L would go in the denominator. Or you could just put A if it makes it less confusing for you to solve. And then you can solve that. Right? So we have 4A equals 9 times 36. I don't care what that is because I'm not going to do that math. I'm going to go ahead and divide by 4. A equals, and I'm going to cancel. A equals 81. You can do it in your calculator. That's totally fine. Like I told you guys earlier, but so the area, I'm going to add my L in there, my sub L, area of my larger prism equals 81. It's area, so I need to use that, put my units squared on there. Oh, I moved my whole thing there. Sorry about that. All right, my units squared. So now I have finished A. I did all the parts of A. Now we're going to go on to B. Yeah. Okay, so let's look at B. This one, okay, this time it says find the ratio of their volumes. So it'll be cubed this time. So we take the ratio of their sides, this 2/3 again. So 2/3 to the power of 3. So again, that's 2/3 times 2/3 times 2/3. Anybody agree with 8/27ths? Okay, so 8/27ths is our first part there. So this is the ratio of our volume. Good, so now we want the proportion to find the volume of the smaller one, which is the V sub S. Good. And we know the volume of the larger prism, V sub L, is 1,215. Okay, so we're going to bring that ratio of our volume of our prisms down. Okay, because this is the volume of the larger one. It'll go on the bottom, yes, because that's the larger prism. Okay, so this is going to be our volume of sub S, of the smaller prism. And then we solve. Yep, we solve our proportion. So 8 times 1,215 equals 27 V. Divide by 27. So our V, 8 doesn't go, 3 doesn't go into 8. Huh. It goes into 24. So this one I would use a calculator, like nothing cancels easily. So I would use my calculator and check that one. Okay. How about just do 8 times 1,215 divided by 27, and what do you get? Go ahead and do the division, like do the whole math. Okay, so see, then we have the same answer. Like you guys are giving me intermediate answers. So this would equal 360. Okay, and I'm going to label this is my volume sub S, right, for my smaller one. What's my unit on that 360? Units cubed. There's a little bitty 3 in there. Gosh, doggone it. So, I'll make it a little better. 360 units cubed equals the volume of my smaller rectangular prism. I don't know, Junior and Leah, I didn't hear very much from you guys. What are you thinking? It makes sense. Okay, so can I go ahead and erase? Yeah. Okay, let me see if I can line my thing back up here. My bar keeps moving. Okay, so then let's look at the scale drawing model idea and scale. All right, so all in a scale drawing or a model, we kind of talked about this a little bit yesterday. All dimensions are in the same scale or ratio to the actual dimensions of the object. So if we're drawing, if somebody gives you a blueprint of a house, it doesn't matter if you're looking at the length or the width of it, right? It's all to the same scale. If you, have any of you ever gone anywhere and they have maybe like the statue, I think of the Statue of Liberty, the Eiffel Tower. You've seen like the little models of those, right? Do you think that they're to scale? No. Yes, they are, right? Like you could buy a little Eiffel Tower keychain and it may be 1/50th of the size of the actual act, but it's still to scale because otherwise it wouldn't look proportional. You'd have like a really fat base and like a really fat top. Is that how the Eiffel Tower looks? No. You've never seen, okay, picture of the Eiffel Tower? Okay, so the Eiffel Tower kind of looks like this.
Isn't it in France?
It is in France and like has a bunch of stuff out here, like all there's kinds of things here. But I mean like it's really fat at the bottom and it comes up to this really skinny point-ish. Okay, but if both the top and the bottom were fat, would it be proportional? No, right? Or if you've ever gone to a carnival, have you ever walked into like the hall of mirrors somewhere and like you walk up to some mirrors and they totally make you look disproportional? Like it makes the top of your body really fat and the bottom of your body really skinny. Okay, those are not proportional things, right? They're not showing you. But a regular mirror, if you walk up to it, shows you proportion. When you look at your reflection in water, does it show you proportion? Sometimes. Okay, it depends. How about, have you ever walked beside a shiny car and looked at your reflection? Is it proportional? Not usually, because there's curves, right, in the car, and so it changes the way your body looks. That's not proportional. How about, have you ever looked at your face in a shiny spoon?
I've never done that. Flipped upside down and it's dark.
Right? Okay, so if you've ever done that, like it depends. Like if you look at the spoon and then you look at the concave part, it distorts your image one way. If you look at the other side where it's curved, it's going to distort your image differently. So that's the thing, is we have distortions. Scale models do not distort. They keep things proportional. When things are in proportion, they look the same way. Okay? And what this is saying is scale models and drawings, all the dimensions are to the same scale. Otherwise, it distorts them. Okay? So blueprints are to scale. Pictures are to scale when you do them. Like if you take anything on your computer, if you've ever written a paper or you're making a graph and you find a picture online and you take it, but you have to adjust it to fit the size you need. You're adjusting it to scale. Okay, every part of it is getting the same number of times bigger or smaller. Okay, so then scale then is simply the ratio of the dimension to the corresponding dimension of the actual object. Okay, but here's the thing. It's the ratio of the dimensions to the corresponding dimensions of the actual object. So if you use scale of 1 inch to 5 feet, if you think a map or a globe, okay, 1 inch is the model. 5 foot is the actual. That's what this definition is saying. Scale is the model, the image, the drawing, to the actual. Okay, that's what you need to know. Scale, however, can be written. This is super important for you to realize. We can write it as 1 inch to 5 feet. We could make them the same unit. Say, oh, well, 5 feet is equal to 60 inches. So it's 1 inch to 60 inches. If we have the same unit, we don't even need to write the unit. We just take it off because we're kind of lazy like that. Okay, mathematicians don't write things if they don't have to, quite honestly. Okay, and that's what this says. Notice that when the scale has the same units in the numerator and the denominator, the scale is expressed without any units, because then it doesn't matter if you're using feet or it's 1 foot is equal to 60 feet. Centimeters, 1 centimeter is equal to 60 centimeters. Okay, so if there's no units, you're assuming it's the same unit. Okay, all right, so let's look at this example. A toy manufacturer makes scale model tractors with a 1 to 8 scale. If a model has dimensions of 17.5 inches by 11.25 inches by 11.5 inches, what are the corresponding actual dimensions of the tractor? What do we think? Okay, scale models are what? No, scale models are what? Are they similar? Are they congruent? Are they proportional? They're proportional. If things are proportional, what should we set up to solve them? Fractions that make proportions, right? 2 fractions make a proportion. So we need to set up a proportion for each one of these side lengths, right? Like that's it. There's 3 side lengths. We need to set up a proportion for each side length. A proportion is 2 fractions that are equal to each other. Yes. So each of these numbers would go on each of those. So, because this is the model, right? Okay. So that's the other thing. So we're going to write model over the actual. I'm going to write that there to help me. So in my model, I have 17.5 for that length, sure, and 11.25 for this side, and 11.5 for my next side. So do I know the actual size of my tractor? Right? Model is in the numerator. Do I know the actual size of this? No. So I'm just going to like label this one X. Do I know my actual measure of this side? Nope, that's my Y. Do I know my actual measure of this side? Nope, we're going to make that Z. So what the heck goes in the other ratio of the proportion? Not a question mark. Why do you say 1/8?
Because the little tractors are 1/8 of the scale.
Okay, because that's the scale, right? The little tractors, the model tractor is 1/8 of the size of the actual tractor. So in every single one of these, it's just 1/8 is my scale. I'm basing my measurement off my scale for all of them. Okay, I'm going to pause this. I want Hayden and Junior to do the first one, Leah to do the second one, and Ann to do the third one. All right, so this is the answers that we got. 140 equals X, 90 equals Y, and 92 equals Z. I should probably put my other cross on all these so we know. All right, but then the other question was, what unit do these have? What'd you guys tell me? It's 140 inches. Okay, so 140 inches equals X. So 140 inches is my model tractor or my actual tractor? Actual, because X is in my denominator, right? And the denominator is the actual for all of these. Okay, our scale didn't have a unit. Okay, but because we were given our units, we were given these units in inches, then all of these units are also inches. Okay, perfect. Okay, so make sure you're using that scale to write a ratio for your proportion. And a proportion is two fractions that are equal to each other. Okay, all right, then your homework tonight would be to do the problems that we did not do last night. So now you can do all of them. So we stopped at 5, so 7 through 39, and because you already did 17, 19, and 25, and then 43 to 51 odd. Okay, so finish up the rest of those that we didn't already do. Just the odd, just the odd. Good question.